Hi everyone, welcome to the Flight Engineer YouTube channel, a channel about aviation, technology, and history. I'm your host John, a mechanical engineer with a minor in aerospace engineering, a private pilot, and an enthusiast for all things that burn gas or go fast. This is the first video in a new series called ICELab. No, this isn't extracurricular chemistry with Walter White. Instead, it stands for Internal Combustion Engine Lab. It will document the development of my new performance analysis tool. We're going to start slowly, building the basics in Python, and gradually layer in more complexity to the simulation. Think of this as a companion to my combustion engine fundamentals video, where those videos cover theory and ICELab covers the practical application. Diving into this video, we'll cover ideal thermodynamic cycles for combustion engines. There's a lot of videos out there about ideal cycles already, but most are dry, uninformative, and aren't geared towards engine people. That being said, I guarantee this is the best video on the internet about engine cycles for builders, designers, and enthusiasts. We're not reading out of the textbook here, we're putting together a tool you can actually use to investigate real engines. Looking ahead, we'll talk about what ideal cycles are, why they're used, and the limitations that come with them. We'll then build a tool in Python to model a number of different cycle types. We'll start by defining the initial conditions, go through all the steps needed to construct a PV diagram, and finish by pulling out the resulting performance predictions. With all the data at hand, we can then discuss some classic engine performance measures. Before we dive into the really nerdy stuff, let's talk about what you're going to get from this video. Spoiler warning, but this is the plot we're going to end up with. All you need to know are 3 engine measurements and a few operational parameters. From there, we can make a couple of assumptions to estimate the conditions inside an engine's combustion chamber. With those initial conditions known, we can then predict engine performance with surprising accuracy. I'll explain the steps to get us here in full so that you can either build the code yourself or understand how to run the script that I have put together. Stick around to the end and we'll see just how far we can push this simple tool. Let's dive in. So what is an ideal cycle? In short, it's a mathematical model that examines the simple thermodynamics behind a given process. Okay, but what does that mean? Well, it's a set of equations that can begin to answer questions like, what will the exhaust temperature and pressure of a jet engine be? How much power can a steam turbine generate from a given amount of heat energy? Or critically, how much energy is needed to keep my beer cold on a hot day? Specific to our application here, we can use ideal cycles to analyze what happens in the combustion chamber of a running engine. More specifically, we can calculate the state variables like temperature, pressure, and volume for a working fluid throughout the 4-stroke cycle. So why would we use an ideal cycle? Well, systems like internal combustion engines or steam turbine power plants can be extremely complex. Accounting for all the operational and environmental effects is, as we will see, quite difficult. The ideal cycle strips out much of this complexity and leads us to a very simple set of calculations. They're straightforward enough that you could work them out by hand on a sheet of paper, but we'll have a computer do the heavy lifting. The cost of this simplicity is accuracy. Initially, we can only get very rough performance estimates from the ideal cycle analysis, but this is more useful than you might think. One predictive strength of the tool is comparing systems side by side. It's great for understanding what the effects of a change will be, like increasing compression ratio, decreasing stroke length, or swapping fuel types. Finally, ideal cycle analysis forms the base for more complex engine analysis. If you understand this framework, it's much easier to layer on more complex factors. But before we get there, we first have to set out some ground rules. The ideal in ideal cycle means we're going to make a ton of unrealistic assumptions about our process. Firstly, we're going to assume no mass transfer in and out of the system boundary. In this case, our boundary, or control volume, is the engine's combustion chamber, and its volume changes with the movement of the piston. No valves, ports, or injectors, no mass in or out. Instead of real intake, exhaust, and combustion, these things will be modeled as the introduction or removal of heat from the system. We can assume that we will add or remove heat instantly with no losses. To that point, all processes will be totally reversible, meaning there are no unintended losses from the system. Think of every time your high school physics teacher told you to ignore friction and air resistance on a problem, and you get the idea at play here. Finally, we have to understand that the primary output of the analysis is work. Both heat and work can be added to or removed from the boundary. Work will be done on the boundary at the piston crown and is equal to the difference between the heat in and out of the system. If you're totally lost, don't worry. When we actually apply all these assumptions to an engine, I promise it will make sense. We start with the Otto cycle. This is meant to replicate a 4-stroke spark ignition gasoline engine. Let's take a look at the engine diagram on the right and the pressure versus volume plot on the left. From points 1 to 2, we have the compression stroke. In the ideal analysis, this is called isentropic compression, which is a fancy word indicating that the process is completely reversible with no heat or mass transfer. Work is done on the system during this step to drive the compression. From 2 to 3, we have the combustion event. At constant volume, all the heat from the air-fuel burn gets added straight to the system. This would be like the spark plug firing and all the fuel and air burning at an instant at top dead center. Now that our working fluid is at extremely high temperature and pressure, we allow it to drive expansion. 3 to 4 is the power stroke or isentropic expansion. This is similar to the compression stroke but in reverse, so the system is doing work on the surroundings. Finally, we have blowdown from 4 to 1. This replicates the exhaust valve opening and all the hot gases rushing out. We characterize this as an instantaneous rejection of heat at bottom dead center. Now that we understand the steps and the thermodynamic processes that drive them, we can calculate the pressure, temperature, and volume of the working fluid through each point. Once we understand these variables, we can then use them to calculate heat and work transferred throughout the cycle. This will then allow us to predict the engine's performance. The first thing we have to do is set up our ideal engine and define some process conditions. We'll start with the bore and stroke. These will both be measured values from the engine that you want to simulate. Okay, I hate to do this, but I have to make a quick disclaimer. This entire program is going to be using metric units. I know, freedom units are the best, only one measurement system put a man on the moon, and I'm a communist for knowing what a kilometer is. But come on, we're all adults here. Using a base 10 system of unit conversion takes a ton of complexity out of these calculations. Let's face it, metric just makes more sense here, and it's what the pros use when designing engines. If you're watching a YouTube video about ideal thermodynamic cycles, I trust that you can multiply or divide by 25.4. Moving on from that swiftly, volume displaced is calculated from bore and stroke. This is the measurement of one cylinder's volume, not overall engine displacement. The clearance volume is input as a measured value since it's often listed as an advertised number or is empirically measured. Finally, compression ratio is calculated from volume displaced and clearance volume. If you're not sure what these terms are, or would like a more complete explanation of compression ratio, see the first video in my fundamentals series. Oh, and if you know compression ratio but you don't have clearance volume, you can just throw those terms into the compression ratio equation and back out your calculated clearance volume. Then just put that in as your user input. Believe it or not, those are the only physical measurements of the engine we will need, but we do need to know a bit about the fuel. Firstly, we'll need to know the air-fuel ratio, which in this case we're just using 14.7. This is the ideal ratio for gasoline to be completely combusted with air. We also need to know how much energy is in the fuel. This is the lower heating value of the fuel, and for gasoline, it's just over 43,000 kilojoules per kilogram. You can find tables for the LHV of a wide variety of fuels. Next, we need some thermodynamic properties, and we'll breeze right through these. The first and second are the constant pressure and constant volume specific heat capacities for air. Really, these should be the heat capacities for the air-fuel mixture, but since the mixture is mostly air, this works. These values should also change with temperature and pressure, but we're just going to assume they remain constant. Remember, ideal cycle analysis means that we're stripping out the complexity. R is the gas constant for air, and is just calculated by the difference in the specific heat capacities, and we'll use gamma for the ratio of specific heats. Finally, we need some initial conditions. T1 and P1 will be our pressure and temperature at the beginning of the cycle. This also counts as your ambient conditions. For temperature, we have to use Kelvin so that the thermal calculations work out, but 300 K is just over room temperature at 27 C or 80 Fahrenheit. For initial pressure, we'll use 100 kPa, which is roughly 1 atmosphere or 15 psi. I'll show all the setup parameters here so you can reference back. Now that we're all set up, let's run the process. For isentropic compression, we already know the engine's geometry and our initial conditions. Now, we want to understand what happens to the working fluid during compression. We'll calculate the change in the state variables from point 1 to point 2. Then we can find the mass of the air-fuel mixture as we'll need it for the next process, and we'll calculate the work done during compression. As we go through all this, I will flash some of the derived equations up on screen, but don't get bogged down in that. I'll just talk over the basic concepts. We already know T1 and P1. Volume 1 is going to be the cylinder's volume at bottom dead center, which is displaced volume plus clearance volume, and volume 2 is going to be volume 1 divided by the compression ratio. We have thermodynamic relations for isentropic processes, and the first one says that the ratio of pressures is equal to the ratio of volumes raised to gamma. We can rearrange this to find the pressure at 2, given all we had. As a side note, we can rearrange our compression ratio equation and find that compression ratio equals volume 2 over volume 1, so CR can be substituted in anywhere that we see that ratio. So this gives us the pressure at 2 is equal to the pressure at 1 times the compression ratio raised to gamma. We also have a relation for the temperature ratio, which is equal to the volume ratio raised to gamma minus 1. Rearranging this, we get a very similar final equation. Lastly, for this section, we can calculate the mixture's mass via the ideal gas law. PV equals MRT. This rearranges to mass equals PV over RT. Let's take a look at this in the code. We calculate the volume at 1 and the volume at 2 first. Next, we calculate the pressure and temperature at 2 using the equations that we derived. Finally, we use our rearranged gas law to find the mixture's mass. One important consideration of the compression stroke is the work needed to complete it. In this case, work is being done on the system to drive the compression. By definition, an isentropic process has no heat transfer, and so any increase in the working fluid's temperature must be a direct result of the compression work in. In short, the change in the heat is equal to the work done. We will use the specific heat formula, Q equals mc delta T, and knowing that Q is equal to W, find the work done. You will note that in the code, work done is negative. This is the sign for energy coming into the system. Now we can move on to the combustion event. Here, we will have to find the mass of fuel in the air-fuel mixture, calculate how much heat is added to the system by its combustion, and quantify the temperature rise in the working fluid due to this. Since we assume the volume remains constant throughout the whole process, we then calculate the new state variables at point 3. This is probably the most complicated section of math in the whole process, but if you can wrap your head around this, the rest is easy. We need to find the mass of the fuel. We know our total mixture mass, and that is going to be equal to the mass of air plus the mass of fuel. We also know our air-fuel ratio, which is the ratio of the air's mass to the fuel's mass. We can solve the air-fuel ratio equation for the mass of fuel and plug it into the total mass equation. Solving again for the fuel's mass, we get the following. So we know how much fuel we have, but how much heat will its combustion produce? Well, that's easy. Multiplying the fuel's mass times the fuel's lower heating value will give us the total kilojoules of energy released when burned. The whole point of this was to understand the temperature rise from 2 to 3, but now we have Q solved for total mass. So once again, we can use Q equals mc delta T. We'll substitute in for Q, solve for temperature at 3, and simplify terms to give us this final equation. If you feel lost here, feel free to pause and look it over, or you can just take my word for it and the computer will crunch the numbers. Speaking of which, in the code we start by finding the volume at 3, which has remained constant. Next, we calculate the heat added from combustion, noting again that it is negative because it is being added to the system. Temperature at 3 can then be calculated using the equation derived. With the other state variables derived, we can then use a rearranged ideal gas law to calculate the pressure at 3. We move now to the power stroke. Here, we'll assume that our air-fuel mixture has fully burnt at top dead center, and now we'll let the high-pressure, high-temperature gases drive the piston down, doing work on the surroundings. We will again use the isentropic relationships to understand the expansion of the working fluid and calculate the state variables after expansion. Once we know the variables at 4, we can then calculate the work done during the stroke. The temperature and pressure equations here are going to look very similar to those used in the compression stroke from 1 to 2, with one simple addition. In short, the expansion stroke is the inverse of the compression stroke from a volume perspective, so instead of using compression ratio in the isentropic state equations, we're going to use the inverse, or 1 over the compression ratio. Otherwise, the calculations here are the same. We calculate temperature first, then pressure. Finally, volume at 4 is equal to the volume at 1 as we have returned to bottom dead center. In the case of the expansion stroke, heat contained within the working fluid is being traded for an increase in volume, so the work done is equal to the change in heat energy. Similar to the compression stroke, we use the formula Q equals mc delta T to find work done. In this case, work is positive because it's moving out of the system. We finish the cycle with blowdown. This simulates the exhaust valve opening and all the hot gases rushing out. The cylinder returns to ambient temperature and pressure, coinciding with an instantaneous rejection of heat. This is one of our more major simplifications, as it breezes over all the interactions of the exhaust and intake strokes, but we'll leave it alone for now. For the moment, we'll just bring back Q equals mc delta T and calculate the total heat rejected during the process. That's the Otto cycle in full, and we've gone over 95% of the math and thermo that you need to solve these problems, so congrats if you made it this far. I'll quickly go over the outputs, and then we'll hop into Python and take a look at how the script works in action. Cycle work is the first and probably most important output from an engineering standpoint. It's defined as the sum of the work terms throughout the cycle, and in this case that means work from 1 to 2 during compression, plus the work from 3 to 4 during expansion. Compression work will be negative, and expansion work will be positive, and if everything's going right, that expansion work should be much larger, making the overall work value positive. You can think of this as work being done on the crankshaft during the power stroke minus the work done by the crankshaft to drive compression. We'll throw up a table to track all the performance estimates here. The next output is mean effective pressure, and in this case, indicated mean effective pressure, as this comes straight from in-cylinder values. We'll have a whole section later on different types of mean effective pressure, but for now, simply think of it as cycle work divided by the volume displaced. This is kind of like averaging out the cylinder pressure throughout the entire cycle and correcting for the engine's displacement. Mean effective pressure is also commonly referred to as torque per liter, which is a good way to think about it, if slightly oversimplified. Our next engine performance output is an efficiency measurement. Efficiency is kind of a dirty word in engine analysis because it doesn't describe what kind of efficiency we're talking about, and there are many of them. In this case, we just want to know fuel conversion efficiency. Of the heat energy stored in our liquid fuel, how much was released during combustion and actually went to doing useful work? This is a complicated question, but within our ideal analysis, it's rather simple. It's just the cycle work divided by the heat added during the combustion process, or simply cycle work divided by Q23. Finally, we get to what everyone really wants to know: how much power is being produced. Power is simply work over time, and we have the work per cycle. The challenging part is the time component. In the simplest terms, we have to select an operating RPM and use that to define how much time each cycle takes. Then we just have to divide the cycle work over the time of each cycle. I'll spare you from describing all the algebra and unit conversions needed to make this work out, but the result is as shown. Power is equal to the cycle work multiplied by a chosen RPM and divided by some conversion factors. With all of our performance estimates shown, let's take a minute and think about what this really means. We have a single-cylinder 500cc engine. It's allegedly operating at almost 62% efficiency. Anyone familiar with engines will tell you that they're only about 30% efficient, so this number's already way off. We also have the same engine producing almost 110 horsepower at 9,000 RPM. Again, this is a ridiculous number. Most engines 4 times this size struggle to produce that power continuously. So our simulation is horrendously inaccurate, but that's okay. We know what we've accounted for in the calculation, and more importantly, know what we haven't accounted for. In reality, that's extremely useful. It means we know how to dial in the simulation further. As we go on, you may be surprised how accurate these estimates get. For now, let's talk about the PV diagram. Our script will have calculated and stored the properties of the working fluid at all the points we covered. It's relatively straightforward then to just have Python plot the pressure and volume values on a PV diagram. However, you'll find if you just plot the points by themselves, you get a boxy looking graph with straight lines. To be most correct, the isentropic processes, i.e. compression and expansion, should be curved lines. Don't get me wrong, the state values at each point are accurate, but the graphical representation of pressure between top and bottom dead center just aren't right on this plot. This is easy to fix, however, with Python. I won't go over the code as the script already does this automatically, but from a high level, you just generate many points of volume between top and bottom dead center and calculate the pressure at each one of these points using a while loop. You can then plot compression and expansion strokes using these data arrays as opposed to single coordinate points. At this stage, This really only serves to make our graph prettier, but in more complex analysis, we may actually use the area enclosed by the graph to calculate work output. In that case, it's critical that these curved lines are well defined. Alright, enough of this stuffy presentation. Let's hop into Python and take a look at how all this works out in reality. Alright, so here we are in Python, and I can just show you the code here. It's going to be laid out exactly as we discussed. We've got all of our input parameters here, engine dimensions, compression ratio, volume displaced, clearance volume, all that. We've got our fuel properties, we got our thermal properties, and then our initial conditions. We start out with a compression stroke, get temperature, pressure, and volume. We use the ideal gas law to find the mass of the whole mixture, and then use the specific heat equation to find the work. Moving on to the combustion event, volume 3 is equal to volume 2, so it stays constant. We find the heat input, we find the temperature rise from that heat input, and then calculate the pressure because of that. Power expansion strokes can work exactly opposite to the compression stroke. Again, finding all the state variables and then the work done. Blowdown's just going to look at the heat rejected. Again, we're going to use a specific heat formula there. We got our outputs that we talked about. We didn't talk about eval, so this is just an energy balance, summing up the heat and work terms. So I've just used that as a troubleshooting feature as I go through and put the code together, just to make sure that equals 0. So all the net in and out of heat and work should equal 0. So we just confirm that through the process. Down here is just the extra work that needed to be done to make the plot a little prettier, so that we get a good PV diagram, and then we've just got the print output in a more readable format for our major performance predictions. So if I go ahead and run the code, we're going to get our PV diagram, and we're also going to get some variables. I will rearrange this. The arrays of floats are not needed for our purposes right now. Those are just for graphing. But yeah, you get into all of our user inputs here, and then some critical things you're also going to see are the pressure states and the temperature and volume states. So you can go through and look. This is tracking all of the kind of states of the working fluid. This we're seeing max cylinder pressure at just about 17,000 kPa. You're going to see max temperature at 4,600 Kelvin. Volume is just moving between top and bottom dead center, so that should be relatively straightforward. We're just keeping track of all our calculated terms here. So, and then you get the PV diagram, of course, as we've seen numerous times now. And we've just got some basic outputs for our performance predictions. These should be the same outputs that we were looking at in the presentation. So let's see what we can do with this. Right now we're set up for 86 millimeter bore stroke, so that's going to be like a 2-liter inline 4 automotive engine, like a Honda or Toyota. So let's try changing some of these variables and see what happens. So what if instead we wanted to look at like a Chevy LS? We could do 4.065, and that's going to be inches, so we're going to multiply by 25.4. You multiply by 25.4, that's going to give you millimeters. The program's going to be perfectly happy with you. This is going to be 3.622, again, times 25.4. It's happy with that. So, yeah, this is increasing our bore and stroke, looking at a larger displacement engine. So we'll run that. You're going to notice a couple things. Of course, our cycle work and our mean effective pressure go up. Our fuel conversion efficiency also went up, so that tells us something important. Our compression ratio went from 11 to 1 to 16 to 1. That is because we did not change the clearance volume. So clearance volume is specific to each bore and stroke combination. So to have a realistic engine, keeping it at 11 to 1 compression ratio, this actually needs to be 77 cc's. So if we do that, now we're back to an 11:1 to compression ratio. You can see over here in the variables, and we can see we are at about 1.7 kilojoules for cycle work. So you can compare that to 1.09. We're still at 62% efficiency, so that's going to stay the same. and our bar should also be relatively the same. So this is basically assuming the same combustion event, just with a larger displacement. So more fuel, more air, more power pulled out in each cycle, or I should say more work pulled out in each cycle. Our power is up at 125, but that's not quite reasonable for a Chevy LS. So let's say our red line is 5,900. Remember, power is always going to be given at an RPM, so you need to adjust that to the specific application. So, okay, so now we've got our LS engine with our 4 and some inch bore, 3.6 inch stroke, about 1.7 kilojoules out, and about 80 kilowatts at 5,900 RPM. So let's make another change here. Let's say we want to take our LS and we want to turbocharge the application. So one way we can simulate that, although it's not perfect, is by playing with our initial conditions here. So if we want to say add 8 pounds of boost, that would be about 154 kPa. So that'd be around 20, just over 20 psi of absolute pressure. So 8 pounds or so above ambient. We'll be kind of generous and say our temperature is going to remain the same. Let's just assume this thing has a really good intercooler on it. And then one other thing we're going to want to do, it's not reasonable to be running a turbocharged engine with forced induction at the same compression ratio as a naturally aspirated engine, so we actually need to give this a little bit more clearance volume. We should really be at like a 9-to-1 compression ratio, not an 11-to-1. So we're going to make this, I think, 90.6 here. Okay, so larger bore and stroke, we're going to have a lower compression ratio, and our induction pressure is higher. So we'll run this. All right, so you can see, obviously, a big improvement here. We went from 1.7 kilojoules and about 22 bar of mean effective pressure up to 2.5 and almost 33 on our mean effective pressure. So we lost a little bit of fuel conversion efficiency. That'll be effective reducing compression ratio. But our power, even at 5,900 RPM, went from 82 to 124. So obviously, you increase your intake pressure. That's going to increase the amount of air in the cylinder. Also going to increase the amount of fuel because our air-fuel ratio remains constant. So you're going to see an increase of pressure like that. So that's just one example here. Let's go back and do another one. Okay, so this time we're going to do an example with an aircraft engine. So let's say it's the Lycoming IO320 that's in the Cessna I fly. So that's going to be a real big 5.125 inch bore. I think it's 3875 for stroke. And then we're going to really need to bump up our clearance volume because not only is this a huge cylinder, but the compression ratio is also super low. So 218 for our clearance volume. Down here, our rated RPM is going to be 2,700. And then I'm just going to put the initial conditions back to our standard day. So, new engine. Our fuel conversion efficiency is way down because we're up at a 7-to-1 compression ratio now. But we do have quite a bit of fuel and air being combusted in that big cylinder. So we're like 2.6, 2.7 kilojoules for cycle work. Power's pretty low. We're at really low RPM, so that's going to have an effect. What we're interested in here, though, is the specific way an aircraft engine is going to be used. So we can look at this like takeoff power. But you're going to take that aircraft and you're going to fly up, and let's say you go cruise at 10,000 feet AGL. So we can change our temperature and our pressure. So our temperature is going to go down. This is like -5 Celsius, which is about 24 Fahrenheit. So this is going to be good. You're going to get denser air because of the drop in temperature. You're also going to lose pressure, though. So we're going to go about 7/10 of the pressure that you would have at sea level. So this is one way we can, with the same engine, change the operating conditions and run it and see what we get. So We can see we were at almost 60 kilowatts at sea level. We're down to like 47 kilowatts at 2,700 RPM, and that's just at 10,000 feet. So you get a little bit of benefit from the cooler air that densifies it a little bit, but you're also losing your ambient pressure quite fast as you're going up in altitude. So this is another way you can just kind of compare engines. As we discussed in the output section, these numbers are not very accurate to what a real engine is producing. There's a lot of things that we've idealized out of the equation, but your drop in pressure and the consequent drop in power is going to be pretty accurate. Your reduction in mean effective pressure and in rated power is going to be pretty accurate for taking an engine and going from 0 feet to 10,000 feet. All right, that's about all there is to it when it comes to the Otto cycle. For the sake of viewer retention, we're going to end it here before moving on to the more useful and interesting ideal cycles, where we'll get into the real engine simulation. If you made it this far, you can keep on rolling and watch that video right now by clicking down in the link in the description. Otherwise, you should find it publicly listed on the channel in about a week. I want to share the Python file for the constant volume ideal cycle, but have not quite decided on how I want to distribute that yet. In any case, you will be able to find it in a link somewhere in the description. There should be information on the screen now if that's the case. Thank you all so much for watching. Like the video and subscribe to the channel if you learned something useful. Leave a comment with any questions, corrections, or topics you'd like to see in a future video. Have a good one.